So in the flow sheet, first let us take the reactors. So this is the first reactor, this is the second reactor, this is the third reactor. Okay. Then we have a separator, right? We have a separator and we have a feed. Then output of the first reactor goes into the second reactor. Output of the second reactor goes into the third reactor. Output of the third reactor goes into the flash tank. The liquid output of the flash tank is the polymer, which we will take as a product. And this one will be sent to a cooler. And that cooler is over here. We can put a cooler and the cooler can be rotated, icon flip horizontal, and then this one we can reconnect to the destination, and this one is the product. Okay, right. Now let us put it as feed. This one is reactor output, so we can write it as RP1 or R output 1. This is R output 2. This one, let us write it as R output 3. This is the poly outlet, and this is the unreacted styrene, and this one is the recycle stream, which will form later. Now first thing first, let us fix the feed stream. Feed 5000 kg per hour. So this is 5000 kg per hour. Temperature and pressure 25 degrees centigrade on 1 bar. So it is 25 degrees centigrade, 1 bar pressure. Mass fraction. What is the mass fraction? Mass fraction is reactor feed contains 98% of styrene. So this is 0.98. Ethyl benzene is 1.9%. So ethyl benzene is 0.019. 0.07 weight percent of DDM. So 0.0007. And TBP is 0.03%. So it is 0.0003. So that makes it 1, the total mass fraction. So feed is done. Now we have to set the reactor 1. So reactor 1, the pressure is 1 bar and temperature is 120 degrees centigrade. So this temperature, first, second and third reactor works at 120 degree, 160 and 200 degree centigrade. And the entire process operates at 1 bar. So the pressure is 1 bar and temperature of the first reactor is 120 degrees centigrade. And all reactors work liquid phase only. So this one works at liquid phase only. The reactor volume, 3 CSTers, each with volume of 15 meter cube. So it is 15 meter cube And the reaction kinetics, we have already defined the reaction kinetics R1. So we just put it over here. Okay. So that way we have set the reactor 1. So we call it reactor 1. In the same way, we have to define reactor 2 and reactor 3. So what we'll do, we just save some effort by deleting them and copying and pasting them. So copy, paste as reactor 2. So this one, and then again pasting it as react 3. So this is reactor 3, this is reactor 2. Only thing is that we have to change the temperature because all the reactors are similar except the temperature. So temperature of the reactor 2 is 160, temperature of the reactor 3 is 200. So reactor 2 is 160 and reactor 3 is 200. All other options are same. So we just reconnect with this destination. We take its source over here, and then this one we connect to the destination, which is here, and this one we reconnect to source over here. So that way we are okay. Now we have to set the flash tank. Flash tank temperature. What is the flash temperature? Flashed and separated at 220 degrees centigrade. So this is 220 degrees centigrade and pressure is as before 1 bar because the entire process works at 1 bar. And this, it is a cooler, so from 220 degrees centigrade to 25 degrees centigrade because feed enters at 25 degrees centigrade. So we have to put the recycle back to 25 degrees centigrade so that it can match the inlet feed. And this is 1 bar pressure. Okay. So we shall not connect the recycle stream now. Let us run this because all the required input is complete. So let us run this and see what happens. We will close this one. We no longer need it now. Okay. So after the first run, we will analyze the result and then we'll check how to connect the recycle stream back to the process. So let us run. Okay, so these are results with warning. Let us check what is the warning. Okay, here you can see MW or the molecular rate entered for the component TBP is different from molecular rate calculated from the formula. Entered value used is 216.32 because that is the value that we have entered, and calculated value is 146. Okay, there is a problem over here. It is 10 to the power 12, but we have kept it as 10 to the power 10. So we have to change it to 10 to the power 12. And let us run it once again. Okay. Now there is no problem at all. Okay. So for this particular mistake, our results are coming with some warning. Okay. Now let us look at the result summary. Now this is the feed This is the polymer out, this is the recycle loop. So out of 4,900 kg per hour of styrene, that is 98% of 5,000 kg per hour, 4,250.96 kg per hour has come into the polystyrene flow, and 344 kg remained unreacted. Okay, and recycle loop is having 306 kg. So when this poly out is coming out of this system, that means 344.106 kg per hour of styrene is getting lost through the polymer flow. 46.73 kg per hour ethyl benzene is getting lost through the polymer flow. This DDM and TBP are also getting lost through the polymer flow. Obviously, at the downstream, there should be some polymer recovery unit from where the other things can be taken together and sent back as a makeup fluid. But that option is not over here. So we are basically looking at this polymer flow rate and recycle flow rate. So what is the recycle flow rate? You can see polystyrene is next to nil because polymer is heavy and it is going out through the liquid. Through the vapor stream, there is practically no polymer. This is the reactor output 1, this is reactor output 2, this is reactor output 3. And the reactor output, through the first reactor, we have got only 967 kg of polystyrene. That goes up to 3003 kg per hour polystyrene, and that increases to 4250 kg of polystyrene. So how the amount of polystyrene increases from first reactor to second reactor to third reactor. Maybe if we have a fourth and fifth reactor, probably it will be more refined, but it is not needed because probably it will not be cost effective. Now we are at this point. So we have got this recycle, and this recycle stream we can attach to the feed, and whatever we are losing over here, that amount of styrene, TBP and DDM we have to provide as a makeup fluid. So we have to arrange some makeup fluid over here. For that, we need a mixer. So let us take it over here. This is a mixer. And in this mixer, we attach this line. We attach a recycle line. And we attach another feed line. This we name as mix. So this is the mixer block. And this one, we write it as makeup. Okay. Now the policy is that we shall keep the feed to be 500 kg per hour, and its ratio of styrene, DDM, TBP and ethyl benzene will remain same. Whatever is coming through the recycle, let them come, and the rest we will put it as a makeup. So that is our policy. How can we do it? We can use it with a calculator block which is available over here in flow sheeting option. Calculator. Here we define several variables over here. So what are the variables that we'll define? Let us understand them first. We shall define 4 variables over here. Makeup styrene, makeup ethyl benzene, makeup DDM, and makeup TBP. Right? And we will have recycle styrene, recycle DDM, recycle TBP, and recycle ethyl benzene. And we will calculate the makeup ethyl benzene as, or we will calculate makeup styrene as 5000 multiplied by 0.98 minus whatever the recycled styrene that is coming through this. So, in other words, the calculation will be something like this. Suppose we have makeup styrene, which is styrene content in makeup stream, and recycle styrene is equal to styrene content in recycle stream. Then makeup styrene will be equal to 5000 into 0.98 minus R styrene. So this is the calculation that we have to do. Similarly, for makeup ethyl benzene will be equal to 5000 multiplied by 0.019 minus recycled ethyl benzene. So this one we'll put it into the calculator block. Understood? So let us do it that way. First we have to define the variables. Let us define makeup styrene, and this is a stream which is a mass flow of stream makeup and component styrene. Okay. Similarly, makeup ethyl benzene, this is also a stream of mass flow in makeup stream of component ethyl benzene. Then makeup DDM is a stream mass flow of stream makeup component DDM. And then makeup TBP, which is equal to a mass flow of stream component TBP. Right? So whatever the styrene, ethyl benzene, DDM and TBP that is going through the polymer outlet stream, we will make up through this makeup stream. Similarly, we can produce the name of recycled styrene. So RSTY is equal to a stream of mass flow recycle stream styrene. Then REB, that is for ethyl benzene, is a mass flow of recycle stream of ethyl benzene. Okay, and then recycle DDM, this is stream of mass flow in the recycle stream component DDM. And finally, recycle TBP is a stream mass flow stream recycle component TBP. Okay, so all of them have been taken. Now this is an import variable. This is also an import variable because this is imported from the Aspen Plus calculation. So this is also import variable because they are needed to calculate it. Whereas these are all export variable because after calculation they will be exported. So they are exported variable. They are the result of calculation. Now what will be the calculation? The Fortran calculation will write MSTY is equal to 5000 multiplied by 0.98 minus RSTY. Okay. Similarly, RDDM is equal to 5000.0007 into RDDM. MTBP is equal to this into 0003 RTBP, and ethyl benzene this into 0.019 REB. Okay, so the calculation is done. In the makeup stream, we have to give some dummy value. Although this makeup stream, they will be calculated, but we have to give some dummy values. Obviously, the temperature and pressure we have to provide. But here we have to give some dummy value. Let us give 1. This is 1, this is 1, and this is 1. Now these are all dummy values because ultimately they will be calculated by this calculator block. Okay, so makeup stream mass flow of styrene, makeup stream mass flow of ethyl benzene, makeup stream mass flow of DDM, and makeup stream mass flow of TBP, all will be calculated through the calculator block. Okay. Now the system is ready for run again. So run it. Okay. Now see the result summary. Now you see makeup stream. What is the flow? Flow of styrene is 4593.63. What is the styrene flow we have given in the makeup stream? We have given 1 kg per hour. Isn't it? Makeup stream we have given 1 kg per hour, but you see the result stream, it is 4593.63 kg per hour. So this is the result of the calculator block. So this is the dummy variable, whereas this is the actual variable. Okay. So why this makeup stream is coming? Because this much amount of styrene has lost due to the polymer out. Again, polymer out, poly out is taking out 46.7344 kg of ethyl benzene. So that is being made up through the makeup stream. So the lost amount of DDM through poly out is coming back as DDM over there. Okay. So this is how the calculator block works. Okay. Now, what is the task that we have been given? You see, the task is vary temperature of second reactor between 120 to 180 with an increment of 5 degrees centigrade and calculate the conversion polydispersity index MWW and MWN at the outlet of each reactor. So first let us do it for one reactor and then we'll see the second reactor or third reactor. So we have to vary the temperature of the second reactor. So here we have to do some sensitivity analysis, and sensitivity analysis can be done in the model analysis tool. So here in the sensitivity analysis, first we have to manipulate, that is vary, the block variable of reactor 2. The variable name is temperature, right? So temperature in degree centigrade, starting point is 120, ending point is 180. So it is 120 and 180. Increment is 5 degrees centigrade. Okay, so that's how it is varying. Now we have to define a new variable which is polydispersity index of the reactor 1. Okay, this is a component attribute element because this is a polymer attribute of stream ROP1 because this is the reactor output, component polystyrene, attribute is PDI, polydispersity index. Only one element. Then we have MWW of reactor 1. This is again a component attribute for stream ROP1, component polystyrene, attribute MWW, only one element. Similarly, MWN 1 or react 1, that is component attribute stream ROP1, component polystyrene, attribute MWN, element 1. Okay. What else? PDI, MWW, MWN, and conversion. Conversion means how much of styrene has converted to the polystyrene, right? So what is the total styrene? 4,900. And what is coming through the makeup stream? It is 4593.63. This much of styrene has converted. That is the reason it is being sent to the makeup, right? So this much has converted. So this by this. So this is the conversion. So we have to identify, we have to say new, we have to bring in, say, makeup styre, which is a stream variable of mass flow, stream makeup, component styrene, and we will put a Fortran command over here, that is conversion 1 Actually, this is not the conversion that we are looking for. We have to look for the conversion at this end, ROP1. Okay, what is the amount of styrene that is over there, unreacted styrene? So we had sent 4,900 kg of styrene, and ROP1 we have 3,932 kg. So rest of the thing has been converted to polystyrene. So our definition is slightly has to be changed. We will write it as ROP1 sty. Okay, so this is ROP1 sty, and we will define as the ROP1 styrene, and our this one will be 4,900 minus ROP1 sty is it the one? ROP1 sty, okay. ROP1 sty by 4,900. Okay, and we tabulate in the variable list. We write PDI react. We'll write conv1. Then this one we'll write PDI react 1, PDI react 1. Then third one is MWW react 1, and fourth one is MWN react 1. Okay, so that's how we will tabulate the data. Now you check the run, okay, and see the results. Now, do we see any change over here? We are changing the reactor temperature too, but conversion doesn't change. Polydispersity index doesn't change. Neither of the molecular weight changes. Okay, so the results are not varying at all. Okay, that means if we change the reactor temperature, this does not change. That is understandable, right? Because no matter how you are changing over here, ultimately the feed is having the same rate of ethyl benzene, styrene, and all other things, along with the temperature and pressure. The same thing is going inside the reactor 1. So this is in the upstream of the reactor 2. You are changing the reactor 2 temperature, but nothing in the upstream should change, right? Now let us see what happens if the same PDI, MWW, MWN and conversion, if you shift from ROP1 to ROP2, that is the output of the reactor 2 instead of reactor 1, then what happens to this result? For that, we have to go back to the input, and in PDI react, instead of stream 1, you change it to stream 2. MWW react, instead of stream 1, you change it to stream 2. All other definitions remain same. MWN, instead of ROP1, you change it to ROP2. And this one also, instead of ROP1, you change it to ROP2. And now, the tabulation remains same. This one remains same. Okay. Now, this was the result. Now you run it once again and see the changes. Now you see. With the temperature, conversion changes, polydispersity index changes, and both the molecular weights, they change. Both weight average and number average. Because it is the downstream, right? So anything that is affecting the reactor 2, the downstream flow of the reactor 2 will always have an effect of that change, right? So that's what we observe. Similarly, if you change it to reactor 3 instead, then also the similar changes will be seen. You have to just change it to reactor 3 because reactor 3 output is downstream to reactor 2. So here again, run it. The data will change, but the variation with temperature will be visible. Okay. With that, we come to the end of this lecture, and I hope you have enjoyed it, and we shall come back with yet another interesting lecture very soon. Thank you.